Welcome to a new class on classical mechanics. So we are starting this series in order to consolidate your concepts on classical mechanics. So let's begin. So I am beginning with you first the Lagrangian formulation. Okay, Lagrangian formulation. So basically, this is going to be a free session on YouTube. I will be uploading all the lectures of mine consequently, okay, in the upcoming days. So you will have all the access to all my lectures, and you can score good marks in your exams and can have a consolidated concept on the topic. So let's begin. Basically, why we are considering the Lagrangian mechanics and in which way it is better than the Newtonian mechanics. Okay, so we are considering the Lagrangian formulation of classical mechanics, and this Lagrangian formulation of classical mechanics is energy formulation of systems. Basically, Lagrangian is what? We are considering Lagrangian as the difference between the energies, like kinetic energy minus potential energy. You all must have known about this. If you don't know, so no issues. You, I will, I will talk about this. Okay, and it is preferred over Newtonian classical mechanics. Although both give the same results, but the calculation-wise, Lagrangian mechanics is much wiser. So it gives us extra average in order to solve the problems. That's why we're considering the Lagrangian over the Newtonian. So basically, Lagrangian is the function of, let me decrease the pen size. Okay, Lagrangian is the function of q, qi dot and t. Don't confuse between q, qi dot, t, what I have written all this. Qi is basically the generalized coordinate. Generalized coordinate. Wherever you have doubt, you can just comment down on the video, so I can check out. And qi dot is the generalized velocity. Okay, and t is the time. You all know this. And then I have Lagrangian. How can I define this? Lagrangian is defined as t minus p. Okay, this is how we define Lagrangian. Lagrangian is defined as L is equal to t minus p. And then I have most importantly, I have the Lagrangian equation of motion. Let me talk about that. The Euler-Lagrangian equation of motion, and I am not going to derive all the formulation. I am not going to derive the equation, how it derived. You can check the GC by the book. It is a very good book, and for much understanding you can prefer Goldstein. Okay, you can prefer Goldstein, and its problems are very good problems, instant problems. And if I have time, I will try to upload the problem solution videos in my channel. Let's see. But for that you have to subscribe my channel and you have to like all the videos. And generally I am saying, if you are having benefits from my channel, then you could share it with your friends. Sharing is caring. Euler-Lagrangian equation of motion. I am just writing it. Equation of motion. What does it? This is basically dy dt of del L by del Q dot minus del L upon del Q. As you must have a doubt, like why I am writing I in the subscript, because I am considering it as a generalized things. There are plenty of QI coordinates. Okay, are you understanding? Like in 3D, if you are considering the three Cartesian system, so you have x, y and z, three components. Similarly, if you are considering the spherical coordinate system, you have r, theta, phi. If you are considering the cylindrical coordinate system, you have s, phi, j. This is the thing why I am writing this. This is the generalized form. Understood? Let me talk about the generalized coordinate that I have written earlier. Generalized coordinate. When I am talking about the generalized coordinate, that is the number of independent suitable coordinates, to describe the dynamics of the system. You can say number of independent suitable coordinate to describe the dynamics of the system. That's all. And according to your comfort, you can define the generalized coordinates. That's totally upon you, how you are defining the generalized coordinates. And remember one thing, the number of generalized coordinates is equally to your degrees of freedom of the system. Clear? You have to remember this. That's why I have written it in red. Okay, let me give you one example, a very interesting example. Let me give you this. Suppose you have this. Okay, and you have one mass here, you have one mass block here having mass m. So if I will ask you, just pause the video, and I will ask you what is the degrees of freedom of the system. So what will be your answer? Degrees of freedom of the system, obviously 2. Okay, if I am considering this, it will be x1 and this will be x2. Okay, so simple. This one is the wedge. You might have learned this in your 12th or VSc, or you have heard, if you heard physics rules, you might have seen such type of figure in many places. So we have two generalized coordinate system, as we have 2 degrees of freedom. So we can say that the generalized coordinate for this particular case is how much? 2. Clear? Okay. Then come to your generalized velocity. Generalized velocity. What does it mean? Generalized velocity, we denote it as q1 dot, q2 dot, q3 dot, qn dot. Okay. N is the number of degrees of freedom. Then more is the number of degrees of freedom, the more is the generalized coordinate, the more is the generalized velocity, all these things. And you can also define del qi dot divided by del qz dot as del ij. Del ij is nothing but the Kronecker delta. If you are hearing this for the first time, don't be confused. This is Kronecker delta. You are going to use this Kronecker delta many times, okay, in physics, basically. Okay, and remember one more thing, if you are differentiating, if you are partial differentiating the velocity with respect to the position, okay, you are getting 0. Remember this also. Okay. This is your generalized coordinates and generalized velocity. Let me define generalized force, because we are going to use all these in our upcoming lecture series. Generalized force. The force, where basically we denote it as qi, and I am taking the notations from J.C. Upadhyay. So when you go through the book, you will have all the luxuries to go into it. So basically we are defining qi as the generalized force in ith direction. As I am saying qi, so I could say it is the generalized force in the ith direction. Understood? If I'll have to say Qi, if I'll have to define Qi mathematically, so I could say if dotted with your dou L upon dou Qi, where dou L is nothing but your length element in respect to coordinate system. With respect to coordinate system, this is the length element with respect to the coordinate system we are considering. So you might have a question, so what is the length element? Let me define it for you for different coordinate system. Basically we are using Cartesian, spherical, polar coordinate systems and cylindrical coordinate system. Let me define for all of the three. So first is my Cartesian. In Cartesian coordinate system you have dou L, you have xyz as the parameters here, so it will become your dou x I cap, dou y j cap, dou z k cap. Okay. Similarly in spherical coordinate system you have r theta phi. So let me write dou L will become how much? Dou r cap. Okay. Similarly r dou theta cap. Similarly r sin theta phi cap. So you might be wondering, what is this r dou theta, r sin theta? These are the scale factor. I will talk about it. You must have read it in your 3D Cartesian coordinate system or spherical coordinate systems or cylindrical coordinate system. And the third one is your cylindrical coordinate system. Cylindrical, we have S, phi and z. You may define rho, phi, z in different books, different notations, no matter. So that will become your dou L vector will be dou S cap plus S dou phi cap plus dou Z cap. Okay, so easy, so simple. Then we have in Jesse Upadhyay it is written the dimension of generalized force, but people always confuse it with the dimension of force. It is not necessary, mark my words, it is not necessary that the dimension of force is always equal to the dimension of generalized force. Okay, remember this. So next we have this is about your generalized force. We have studied the generalized force, generalized coordinates and generalized velocity. Let me define the kinetic energy then. So we have coordinates, velocity and your force. Then next thing is our what? The energies, the kinetic energy, the potential energy. So in Lagrangian I have defined Lagrangian I have defined as your L is equal to T minus V. Okay. So in Cartesian your T is equal to how much? Half. If I am considering the 3D, so x dot square, y dot square and z dot square, isn't it? In spherical I have T is equal to, I will give a shortcut to remember all this. Don't confuse it with another concept. Okay, I will give you a shortcut, it will be easier for you. This will be r dot square. Okay, This will be r theta dot square. This will be r sine theta phi dot square. Clear? In your cylindrical, we have t is equal to half m h dot square plus second is phi dot square plus z dot square. Clear? In general, if I have to give you a trick, the trick to remember. In general, I have t is equal to half m and the scale factors h1 q1 dot square plus h2 q2 dot square h3 q3 dot whole square. Okay, this is the trick. You need to know this. For this, you have to remember the scale factors, that is h1 h2 h3 in different coordinate system. So this is your generalized kinetic energy, and if I will have to define the generalized momentum and the canonical momentum, so I could define it as generalized momentum. We generally denote it as pi, and pi is defined as del L upon del Qi dot. Is it clear? Let me give you a simple rough work here, mathematical rough work. We know that phi is how much? mv, isn't it? If I will have to differentiate, Lagrangian is what? The kinetic energy, isn't it? Half m b square, the dimension of energy, isn't it? If I will have to differentiate del L upon del phi, Qi dot is what? Generalized velocity, del L by del phi, so you will get what? Half 2 mv, isn't it? mv, that will give you p. Similar thing is here. You may consider it. You might take it as a reference. So this is your generalized momentum. So this is a brief introduction class for you. You might consider it, and let me tell you few more things about the degrees of freedom. Okay, give me some time to make you understand about the degrees of freedom. You might study it in your kinetic theory classes very well. In class 12, so in 12th class, you might have studied it in details. Degrees of freedom for different gases, gas molecules. If it is one dimensional, if it has 1 degree of freedom, 2 degrees, and 3 degrees of more degrees of freedom. Okay. So let me give you a simple idea. Let me give you some cases, and you will have to tell me what is the degrees of freedom for those cases. Okay. So I know I always want to be a one-to-one corresponding class. Let me give you one scenario. You have to tell me. Okay. So let me give you one scenario. An insect is moving on a thin rigid rod that is flying in the space. So I have the case like this. No need to write the question. I have told it. Okay, let me erase it. Let me also erase it. So there is a three-dimensional rigid rod. Okay, in free space, and an insect is sitting on this rod, and let me define the coordinates. This is your x, this is your y, okay, and this thing is your z. Clear? So what will be the degrees of freedom? That's the case. What will be the degrees of freedom of the system? That's the question I have to answer. Degrees of freedom of the system, isn't it? That will be the degrees of freedom of the system. So as you can imagine this, so the degrees of freedom of the system will comprise of the two things. One is your degrees of freedom, let me denote degrees of freedom in short as F. So it will be the degrees of freedom of insect which is sitting on the rod, and the rod itself, degrees of freedom of the rod itself. That will be the total degrees of freedom of the system. So when I am considering the degrees of freedom of the insect, okay, good. We have to first consider the degrees of freedom of the insect. Let me tell you, the insect on the rod can move along which direction? It can move on the plane. No, it is not going away from the rod. It is just sitting on the rod, and it can move on the plane only. It can fly. Okay. So my degrees of freedom is the translational degrees of freedom plus if what is the insect has the rotational, if it has the rotational, but here rotational degrees of freedom is 0. Here rotational degrees of freedom is 0, so we can neglect this. And what is the translational degrees of freedom? This is 2, so I can say the degrees of freedom of the insect is 2. Then next I have the degrees of freedom of the rod, in which direction the rod can move. The same scenario, I have the translational, then I have the rotational. Okay, if I am considering the translational, see, the rod can move in all the three directions, that is along x, along y, along z. But in case of your insect, it can move on the plane only, on the xy plane only. It can move in the z direction because it is itself in the two-dimensional rod. But the rod itself can move along all the three directions. So I have the translational degrees of freedom of the rod as 3, and it can rotate along the two directions. That is, it can rotate along about the two axes. So that is 2, isn't it? We don't include motion along x-axis because rotation about x-axis is negligible compared to motion about your y and z axis. Clear? So my degrees of freedom of the rod is 5. So my system, the degrees of freedom the system have is 5 plus 2, that is 7. Clear? A very simple example. It may come in your exam. You have to analyze the situation, then you can correctly answer the question. So I hope you like this lecture. So that's all for today. Thank you for your support. Thank you, and do share, like and subscribe. Thank you, friends.